Welcome to Dr. BT's Chemistry Essentials, A-level chemistry made easy. In this video we're going to be starting to look at weak acids and the key descriptors and equations that are used to work out both the hydrogen ion concentration and therefore pH of a solution. If you do find this video useful, ensure that you like it and then ensure that you subscribe to both the channel and leave comments on any new topics that you want me to cover in subsequent videos. So we've already looked in previous videos on what an acid is and the two different types, strong and weak. We know that strong acids are fully ionizable in solution. So if you take an acid HA, all of the molecules will ionize to form H plus and A minus. So therefore, for a monoprotic or monobasic acid, the concentration of the initial acid used gives you the concentration of the hydrogen plus ions. It's really useful because you can work out what the pH of that solution is, because if you've got that concentration of the hydrogen plus ions, you can work out pH by minus log of that value. Now, weak acids are different. They themselves are partially ionized. Show this with the acid, that weak acid, it breaks down into H plus and A minus, and we show the fact that it's only partially breaking down with a reversible arrow. Now obviously we need to work out the concentration of hydrogen plus ions in the solution when the weak acid ionizes, because that's going to allow us to calculate the pH, and that's really important, as we've talked about in previous videos. So we need to know to what extent does the acid, the HA, ionize into H plus and A minus. Now, if we took the simple example of R being reactants and P being products, and it was a reversible reaction, then we could quantify to what extent at equilibrium this lies on by the use of Kc. Now, Kc is a measurement or ratio of the concentration of the products divided by the concentration of the reactants. We take this model, but this time for our weak acid generic setup, then what we're going to do is call this Ka, where A stands for the acid dissociation constant. So Ka as an expression becomes the products, the hydrogen ion and the A minus ion, over the reactant, which is the weak acid. This is just a specific example of a Kc equation where we've got product concentration over reactant concentration. Hopefully you could start to see that because we've got H plus as a term here, we could rearrange this to make H plus the term. That gives us the concentration of H plus from our HA, and then with H plus we can work out pH using that equation. In order to do that, you need the initial concentration of the weak acid that you put into the system, and you need this value here, a Ka, which would describe to what extent this equilibrium is shifted towards. Now, if we have a high value for Ka, then that means we have shifted to the right-hand side of this equilibrium, which therefore means we have a higher concentration of the H plus ion and the A minus ion. So this term is greater. And if we think back to this equation here, if we have a higher amount of H plus, because of this negative, it does the inverse and so gives you a lower pH. And this is really key. It means we therefore have a strong acid. So when you're looking at questions, if there's a higher Ka value, then it's a lower pH is given because more of it is ionized onto this right hand side. And we have more H plus, lower pH. Important term to know is pKa. pKa is used more so than Ka because Ka can be a very wide range of values, whereas pKa, as we'll see now, is actually a logarithmic version of Ka. So if we want to get a value for Ka and express it as a pKa, then what you need to do is do it to the minus log Ka. And vice versa, if you want to take pK and make it into Ka, very much so like pH, what you need to do is take to the power of 10 minus pK. So again, Just like if you have a high level of hydrogen ions, because of this minus, you have a low pH, so this relationship here. If you have a high Ka, because of this minus, you're going to have a low pKa. So this is another really important relationship, because depending on the question, you could be given a value in pK or Ka, and you need to be able to convert between the two. So we're going to take a moment to apply this to an exam style situation. So what I want you to do, you have seen this if you've watched previous videos before. However, I'm going to get you, whereas last time I gave you a hint to help because you hadn't come across this, right now you're going to have to use some information from the previous knowledge in order to work this out. So pause the video now and have a go. Okay, so the answer I'm going to put up and then explain through. So this answer has come from a couple of different things. So you need to understand conjugate acid and base pairs in order to answer this. And then also both the ethanoic acid, this molecule here, is a weak acid. And whilst it's told as a weak acid, we should also know that because they've given us a Ka. And Ka only ever applies for weak acids. So we don't actually need this detail here because it's intrinsic by having these two values given. If you're given pKa as well, that also means it's a weak acid. What you therefore need to do to work out the conjugate acid-base pairs is find out which one of these is the stronger acid in the presence of the other. And you can see here that we have 1.75 times 10 to the minus 5 is a smaller number than this to the 10 to the minus 3. With that, we know from previous that the higher the Ka, the more acidic something is. And we know that that means in practice that if something's acidic, it donates a hydrogen plus ion. So with that in mind, the fluoroethanoic acid, this molecule here, is our first acid. This, in the presence of the ethanoic acid, is going to lose this hydrogen. And it does so, and if you track that change, it's lost that hydrogen there. So that hydrogen, this form of it is the acid form, A1, and it's a pairing with the conjugate base form of it, B1. If you're not sure about conjugate acid and base pairs, watch the first video in this playlist that looks at acid and bases in general. Because this is less acidic, because it's a lower Ka, this one is going to actually take the hydrogen that comes from here, and you can see this in this form here. So this is acting as a base on this side to pick up a hydrogen, whereas on this side they're also a pair. If you lose that hydrogen, then it forms the ethanoic acid. Okay, another exam question for you to have a go at. Pause the video now and see if you can come up with an explanation. Okay, so the explanation you should give is revolving around the fact that whilst they both have the same concentration, the nitric acid and this nitrous acid give different pHs. So it can't be the amount of H plus ions alone in terms of dilution. It must be to do with strength of the nitric acid compared to the nitrous acid. And the big giveaway here is that nitrous acid has a pKa. And we said before that as soon as you see that, it means it's a weak acid. If one isn't given a pKa or a Ka, like in the case of nitric acid, then this must mean it's a strong acid. And so this informs your explanation here. It's a simple application of some of the information that you've learnt, but again, these are easy marks to pick up. Okay, now we're going to go to the final bit around how we use this equation here in order to work out pH. So in the following videos, we're going to be looking at actual calculations. But a usual question for weak acids is that you're given two pieces of information as the given values. You're given the initial concentration of the weak acid, HA. So we're going to have this value here. And then we're also given a Ka. Or you're given pKa, which you can convert into Ka. And so you have two of these pieces of information. Now we know that we need to work out pH, and to work out pH you need the hydrogen ion concentration. So we're trying to work out this term in the equation, and we're going to rearrange that in order to get this. But already you can see there's an issue here. A minus isn't given, so we need to find some way of working it out, or we need to remove it from the equation. And this is the next part of the explanation. We're going to convert this into something that's more user-friendly, but we need to take two assumptions. The first assumption is that the concentration of the H plus equals the concentration of the A minus. So when we think about it, every weak acid molecule, if that was to break down, you'd get a 1-to-1 ratio of H plus to A minus. So on the surface, that seems absolutely fine assumption to make. However, this isn't quite right, because there is another source of H plus ions, and that's the water that's in solution. Water, when it's in solution, as every weak acid is an aqueous solution, some of the molecules, very small amount, but some can break down and ionize into H plus and OH minus. This is exactly why electrolysis allows you to separate water. So the concentration of H plus is always slightly higher than it would be of A minus, but we're not going to let that worry us. It's only a very small effect. So this means that with this assumption, we can say that these two terms are exactly the same. We don't need any information about how much of the salt, A minus, is in solution, because we can get that from the fact that H plus squared is exactly the same as these two terms. So that's our top level. The second assumption that we make is that the concentration of the weak acid that we start with, the initial concentration, is exactly the same at the end as well, so on ionization. Basically saying is that the ionization of HA is such a small occurrence, so even though the weak acid is ionizing into H plus and A minus, maybe only 1-2% of the molecules are doing that because it's a weak acid. And so we can basically ignore any changes in the concentration of the HA that we initially put in that solution. And so the bottom term here is exactly the same that you start with in solution. Now the problem with this second assumption is that it doesn't really work for stronger weak acids. This is due to the fact that if you're a strong weak acid, then obviously more of the HA will ionize into H plus and A minus. So the disparity between the HA concentration initially and at the end is greater. So that's something worth knowing, because you might be asked to comment on that in the exam. But both these assumptions lead us to this really useful equation now, okay? Because as I said, you're given the weak acid initial concentration, you're given some sort of information, whether it be Ka directly or the pKa, and so we can rearrange this to get H plus as a term. And when we do, we get this form of the equation. H plus squared, the thing we need to work out to get pH, is Ka times HA. All I did was move that over there. And then, obviously, pH calculations just require H plus. So in order to get to just H plus on its own, we're going to have to take the square root of all of this side. And then with that answer, we can put it into this equation and get pH. Now, I would recommend learning this equation here, as this is the most useful form of the weak acid equations, and just feeling confident that you can rearrange it to get the different terms here. As I said, the most likely scenario is that you're going to work out the pH of the weak acid, and so you're going to have to rearrange this to make H plus squared the term, take the square root and get to this point. But rather than learning just this, it's important to be able to learn this, because sometimes you might be given other information and, for example, asked to work out the Ka from some other information. Okay, so if you've been watching the videos in order, you should have looked at strong acids and weak acids. And what I'd like you to do now is pause the video and brain dump everything that you know, including key equations and key pieces of information for both strong and weak acids. Pause the video now and have a go. Okay, so I'm just going to summarize the key bits over the past couple of videos. First, I'm just going to put the information for pH and H+ concentration, because these are intrinsically linked, and we know that lower pH has more H+ ions in solution, so the concentration will be higher, and therefore is more acidic. Now, depending on whether or not you're dealing with strong or weak acids, you've got to find a way into this concentration of H+. So weak acids, they dissociate by a minute amount, maybe 1% or 2%, into the H+ and A- ions. They have a Ka value, of which we can represent with those two assumptions as this formula here. But usefully, we often, to get H+ concentration, we need to rearrange this and take the square root as a result. Then that allows us to work out pH through this. Weak acids are identified not only by the fact that there are certain weak acids out there, any carboxylic acid or anything given with a Ka or a pKa, they're interchangeable. So if we have a high Ka, it means this is more shifted to the right hand side, so it's more acidic. And because pKa is the minus log Ka, then that means that a low pKa gives a high Ka, which is high acidity, high hydrogen ion concentration, and therefore lower pH. So lots of things linking together here. Then with strong acids from previous, they're a bit easier to work out. So with strong acids, because they're fully ionizable, whatever the initial concentration of that strong acid you start with, you're going to have on ionization the same concentration of H+ for monoprotic acid. If you remember, if it was diprotic, you get twice the amount of H+, triprotic, 3 times the amount, but often in the exams you're just using monoprotic acids. And so that's really easy compared to this more long-winded approach, because as soon as you've got H+, you can stick into this equation here. So this just gives an overview. You may have laid it out differently, that's absolutely fine. But what you really want to be aware of is that you've got different routes into different parts of this topic depending on the scenario given. And your job in the exam will be to read a question and work out, are you dealing with strong acid? Are you dealing with weak acid? What terms have you been given? And what's the goal that you need to get? Which is often, in the more straightforward cases, the pH. But those weirder cases are what we're going to be going through, especially with weak acids, in the next video. So in this video, what we've been looking at is weak acids and some key terms. If you found the video useful, ensure that you like it, ensure that you subscribe to the channel, and then also leave any comments as to new videos or topics that you want me to cover in the comment section of this video, and I'll get round to doing them as soon as possible.